Welcome students, I am Raman Singh Chauhan. Today we will be taking on the topic Michelson interferometer. Interferometers are devices employed in the study of interference patterns produced by various light sources. An interference works on the principle of superposition. Michelson designed an interferometer to determine the wavelength of light. So here we will talk about Michelson interferometer. Interferometer is a device which is employed to study the patterns of interference produced by various light sources. And here this interferometer was designed by Michelson, and so this is called Michelson interferometer. And the building blocks of this interferometer are monochromatic light source, detector, two mirrors, one semi-transparent mirror that we will take on one by one in the upcoming slides. So this is Michelson interferometer. We can see general diagram. Here we can see this is light source. There are one plate is here, another plate is here, and in place of this a lens is used. This is movable mirror, this is fixed mirror, and when light ray comes from here, then it is splitted on this plate which is called beam splitter, so and reflected towards this side which is called a detector. So we will take on one by one all the parts. So here we can say that interferometer produces interference fringes by splitting a beam of monochromatic light so that one beam strikes a fixed mirror and the other a movable mirror. When the reflected beams are brought back together, an interference pattern results. How interference pattern results, we will see in it here, and we will understand how interference pattern is formed. So here there is a compensatory plate is also there. So that compensatory plate compensate the excess path, because when we are using a diagram, we have one mirror here and another mirror here, and if a light ray is coming here and getting reflected, going to the mirror and vertical mirror, and then coming back to the same path and then going to the telescope that we will see, then this length is traversed by the light beam twice, and when it is directly going to the mirror horizontal, then there is no plate, then there will be a unnecessary path difference will be created, and to compensate that path difference, a compensator or compensatory plate of same thickness and same material is used for compensating or balancing the path, excess path which is traversed twice the thickness by the light beam. So in this way this compensator is important, and that compensates or balances the excess path traversed by the light in vertical direction. So here we can see the diagram, level diagram of this Michelson interferometer. Here we can see this is light source, this is some glass plate, or we generally use a lens here G, this is convex lens, and at this lens focus the source of light is there, and this is monochromatic light source S. Now there is a plate B which is beam splitter plate. On the back side of this plate B there is silver polish, or we can say this plate B made a transparent mirror so that 50% part is reflected towards M2 and 50% part is transmitted towards mirror M1. There are two mirrors M1 and M2, mirror M1 is fixed and mirror M2 can be moved. This is given on a trolley so that it can be moved, and there are scales to measure the position of the mirrors M1 and M2. These backside, these are screws are provided for leveling the or for adjustment of mirror plane. So these are also important because these screws will show in subsequent section of this presentation that how these labeling of mirror or how adjustment of this plane mirror plane will change the formation of fringes by the Michelson interferometer. Now this is the compensatory plate. So here again we can see that when light is coming from the source, it is coming here and it is getting splitting from this back side of this plate B, which is also called beam splitter plate. It is going towards mirror M2 and then coming back to this point and again going to the telescope. This is telescope which is used to observe the fringes. So in this way we can see that from here going to the mirror M2, the thickness is crossed once, then when it is coming from M2 to this point of reflection and then going to telescope, another time the thickness is crossed. And if this plate C or compensator C is not there, then in this ray which is going which is transmitted towards mirror M1, there will be no plate, then this additional path equal to the thickness of the beam splitter plate will be giving some unnecessary pattern, some error because of this unnecessary path difference because of this beam splitter plate thickness. So to compensate this path or to balance this path, another plate of same thickness and same material C is provided in between the beam splitter plate B and the mirror M1, so that when this light ray which is transmitted towards M1 is going, then it is passing through the compensator once this thickness is covered one time in going, and then again it is reflected and coming back, then it is again passed. So this thickness is crossed two times by the beam, and hence this excess or unwanted part difference is balanced and the light ray returns to the plate B, and from here it gets reflected and move towards the telescope. So here we can see one ray is coming from M2 and another ray is coming from M1, this red line. So these two rays, when they are going to the telescope, they gets overlapped, and since these two rays are splitted from one original light beam which came from source S and get splitted into two beams, one ray going towards M2 and one ray going towards M1, and then they are coming back and getting overlapped. So we can say these are two coherent waves because they are splitted from one original light beam, and when these coherent waves gets overlapped while going to the telescope, the pattern which is formed because of this overlapping or superposition of two coherent waves is interference pattern, and that pattern can be seen in the telescope, and what fringes we will see, that we will see later on. Now we will talk about theory. In theory, we know that the condition for minima can be determined to be 2d cos theta m, where theta is the angle between, or if we are going there, then we can see when this mirror M1, we see the rays coming towards telescope, then we can observe that image of this mirror M1 will be seen somewhere in the front side here. And then we can say, suppose a source S is coming, light is going to this mirror M1 and then reflecting. So there the angle which will be formed, that angle is theta. And here for arbitrary order m, it is represented as theta m. So we can say 2d cos theta m is equal to m lambda is condition for minima, and where m is order of fringes, m equal to 0, 1, 2 and so on. And similarly for maxima, we have 2d cos theta m is equal to m plus 1 by 2 lambda, where m is equal to 0, 1, 2 and so on. This is for maxima. So order of the ring, when the central fringe is dark, the order of the fringe is m is equal to 2d by lambda. Here, because when we are observing at the center, then theta will be 0, and when theta is 0, cos theta is 1. So we have 2d is equal to m lambda, and from here m is equal to 2d by lambda. As d is increased, new fringe appear at the center and the existing fringes move outwards and finally move out of the field of view. For any value of d, the central fringe has the largest value of m. So what is d? D is the path difference between, or d is the spacing between mirror M2 and the image of mirror M1. So we can observe this, we can determine this by using the scales provided in the Michelson interferometer. The difference of the scales gives the value of d. Now we have 2d cos theta m is equal to m lambda for dark fringe. So for central dark fringe, because we have theta m is equal to 0 degree, so cos theta will be 1, and so 2d is equal to m naught lambda. The first dark fringe satisfied 2d cos theta is equal to m minus 1 lambda, because now we are moving outwards. When m naught fringe is observed at the center, or mth order is observed at the center, then what we can say, at the center the angle is 0 degree, and with angle is 0 degree, because we know d is fixed and lambda is fixed. So for cos 0, the value of cos theta m will be maximum, and hence m will be maximum. So at the center we will observe the highest order fringe, and as we are moving outwards, theta will increase from 0 to 90 degree. So in that case, cos theta will change from 1 to 0. It means the value will decrease, and hence we can say, if order at the center is m and we are moving one fringe outside, then the order will be m minus 1. So we have 2d cos theta is equal to m minus 1 lambda, and for a small theta we can find out, or we can show that 2d is equal to 1 minus theta square by 2, which is equal to m minus 1 lambda. From here, 2d is equal to minus theta square by 2 is equal to m minus 1 lambda. The radius of nth dark ring can be determined, where d theta m square is equal to m naught minus m lambda is equal to n lambda, where m naught is in case of central order fringe at the center, then we can have m naught minus m lambda is equal to m lambda n lambda, because m naught and m are integer, so n is again integer. So from here we can see that Rn square is proportional to d square theta m square, which is d square n lambda by d. This can be determined. Now we will find, or we will see how the fringes are formed, or what type of fringes are formed in Michelson interferometer. So first of all, circular fringes are formed, and when circular fringes we are talking of, then what we have, when the mirror planes of M1 and M2 are normal to each other, then the image of mirror M1 and M2 will be parallel. and when the image is parallel, then a air thin film will be formed of uniform thickness, and in that case, if we will observe the fringes, then we will have circular fringes here, and for those circular fringes, the path difference can be determined, and the path difference will be 2d cos theta is equal to n lambda. Now, for curved fringes or hyperbolic fringes, there are two types of hyperbolic fringes we can form. In one case, when on the left side the thickness is decreasing, then m1 and m2 dash, where m2 dash is image of mirror m2 and m1 is mirror m1. So, in that case, this type of fringes will be formed, means hyperbolic fringes will be formed, and the curved part will be like this as shown in the figure. But when on the right side, the thickness is decreasing, then the pattern will be opposite of this original pattern. So, we can have such type of hyperbolic fringes or curved fringes. Now, straight line fringes, when we will be taking the intersection point, then at the intersection point we can see, we will observe the fringes in a straight line. So, these are called straight line fringes, although these are hyperbolic fringes, and we can see these. So, these will be formed, these hyperbolic fringes will be formed when the mirror plane of the mirror M1 and M2 are not normal to each other, not perpendicular to each other. In that case, a virtual air film of non-uniform thickness will be formed, and if we are observing at a intersecting point, then we will have straight line fringes, and when we are observing away from the intersecting point, if we are going toward this side, then we will have the pattern of hyperbolic fringes, and again if we are going on this side away from this intersecting point, then again the opposite type of hyperbolic fringes will be observed, or curved fringes will be observed. Now, we will see one application of Michelson interferometer, that is determination of lambda from circular fringes. So, circular fringes are used to determine the wavelength of the source of light. So, for determining the wavelength of light, we can use the Michelson interferometer, and what we do, in the beginning we set the interferometer at the central position, and suppose at the central position the order of the fringe which is at the center is nth order, and so we have 2d is equal to n lambda as the condition. And now if we move mirror M2 to some distance, then the path difference will be changed, and if this distance is delta d, then a path difference of delta d is created in between the fringes, in between the thickness will be changed by delta d of the virtual air film. So, we can observe that when we are moving the mirror M2, the fringes will change at the center. They will shift by some order, they will appear or disappear. If we are increasing distance, if we are moving mirror M2 away, then we will find that fringes are appearing, the center fringe will come out, and another fringe will appear at the center. And similarly, we can count the number of fringes one by one while moving the mirror M2 by distance delta d. And if we are decreasing the distance of mirror M2, then in that case the central fringe will disappear, and the next order fringe which is outside will shift to the center, and in that way we can again observe the disappearing, and we can count the disappearing of the fringes while changing the distance delta d. So, in both the cases whether the rings are appearing or disappearing, as we are moving the mirror M2 at the center, then the path difference after moving the mirror is given as 2d plus delta d is equal to n plus capital N lambda, where capital N is number of fringes which appear or disappear while changing the distance of mirror M2, and hence by using these two equations 2d is equal to n lambda and 2d plus lambda d plus delta d is equal to n plus capital N lambda. So, from here we can determine the wavelength lambda to be lambda is equal to 2 lambda d 2 delta d over n. So, by knowing the value of delta d, because we know experimentally that this distance we have changed and this distance is changed to the mirror M2. So, we know this distance as and n capital N, we counted these number of fringes, we observed this appearance or disappearance of fringes from the center. So, we know this n also, and from here we can determine the wavelength of lambda by using these values. So, this is all for today's class, the Michelson interferometer. Next topic we will consider in next class. Thank you.